This question is about a contact force and says this. In the diagram, a person pushes on the larger box towards the right. You can see that represented by the arrow. The coefficient of static friction between the boxes and the floor is 0.35. Determine the maximum horizontal force the person can exert without moving either box. They're touching each other, and so you're going to only move the one if you move the other. Part B says calculate the force that the larger box exerts on the smaller box. In part C, if the person can push with a force of 350 newtons to the right and the coefficient of kinetic friction is 0.3, what will the acceleration of the two boxes be? So let's do this starting with part A. Determine the maximum horizontal force the person can exert without moving either box. And so I've labeled that as FA. Now, we generally draw those forces on the middle, from the middle and out. And so let's redraw that like so. From the middle of that 52 kilogram box to the right, it's pushing it to the right. And let's now add some other forces to this. Because it's not going to be moving, there's a static force of friction, and it's the maximum static force of friction on that box. We're going to label that as 1 because we're going to call that 52 kilogram box, box 1. Now for box 2, the smaller box, that is the force, there's a force that big box exerts on the smaller box. We're going to call that the force of 1 on 2. And then there's going to be this equal and opposite reaction force, according to Newton's third law, of that second box back on box 1. So that's F2 on 1. Now we're going to draw the Fs max on that second box, because again, that one also is not moving. It's the maximum static force before it does move. And so now we can look at the vertical components. Vertically, we have the force of gravity acting on both of those boxes. Because they're sitting on the surface, there's a normal force being exerted upwards on both of those boxes. Now that normal force is equal and opposite to the forces of gravity because we know that there's no acceleration vertically. So we're going to say now that to the right is positive, just to make things a little more simple to substitute in. And if it were to accelerate, it would accelerate in that direction, which it's going to do in part C. For now, it's not going to accelerate, so let's keep that in mind because it's the maximum horizontal force without moving the boxes. Now you'll notice I've circled those two forces, the internal forces, the force of 1 and 2 and 2 on 1. Because those are internal forces, those cancel each other out on the system as a whole because these boxes are going to try to move together. So we draw the system free body diagram, which is the mass of the entire system, both boxes combined, and the force of gravity total is acting down on that, and the normal force is acting up on that. Now, horizontally, that applied force that I'm pushing to the right with is acting on both boxes to the right. We'll call that FA1. And then we have this maximum static force of friction that's acting on both boxes, so we'll call that the Fs max total, T for total. Now, what we do now is we go through our givens and requireds, analysis, solution, and statement. The givens are that we have mass 1 is 52 kilograms. That's the one that we're pushing to the right on. The mass 2 is the 34 kilogram box. And then the total mass is the sum of those, which is just going to be 86 kilograms. And the required value that we have here is we are required to find the applied force that is going to be exerted, the maximum force to just not move the box. So it's FA1 that we don't know. So we always start with going from our system free body diagram now with our analysis to our equation F net equals ma, which is based on Newton's second law. So F net equals ma, and that mass better be the same mass there as the mass of the free body diagram we're referring to. Because it's the system free body diagram, it's the total mass. Now the acceleration is 0 because it's not going to be accelerating. So we break down the net force into the two forces. There's only two forces in the direction that we're trying to accelerate it. And so what that means is that those two are the only two forces that sum to 0. One is the negative of the other, or we could say the magnitudes are equal. So we're just going to break this down. We're going to get rid of the vector signs here because we know those are equal and opposite forces. So we're just going to look at the magnitudes for now. So FA1 is equal to Fs max total, but Fs max total is also mu s times Fn, and that's the total normal force. But there's no acceleration vertically. And because there's no acceleration vertically, just like there's no acceleration horizontally, that means that the normal force is equal to the force of gravity. The magnitudes are equal. They're equal and opposite forces. Magnitudes are equal. So then we break down the force of gravity. It's always equal to the mass times g. And again, it's the total, so we're using the total mass. And now we can go ahead and sub the values in. I hadn't written down my given of the coefficient of static friction of 0.35, which I've now done. I sub that in with my mass of 86 kilograms, and G is always 9.8 meters per second squared. And then I can continue that, and I get an answer of 294.98 newtons. Now what I want to do in my final statement is I want to go ahead and put that to the proper number of significant digits and reflect on, does this answer make sense? So here's my statement. Therefore, the maximum horizontal force without moving either box is going to be, how many sig digs should it have? It should have 2 significant digits because the masses and the coefficient of static friction are both the 2 sig digs. So we write that as 2.9 times 10 to the 2 newtons, and this is to the right or forwards in terms of the diagram that I've drawn. You could say either of those, right or forwards, both are correct. So we take a moment just to reflect on if that makes sense. The applied force is equal and opposite to that Fs max total, and so if the Fs max total is 294.98 newtons, so is the applied force. All right, part B now says, calculate the force that the larger box exerts on the smaller box. And so now what we're going to do is we're going to zero in on that force 1:2, the larger box on the smaller box, which means that we're going to use the free body diagram of the second box. We have the same givens and requireds as before, but for our analysis, we're going to start with F net equals ma, but notice that the mass is different. The net force is the net force on the second object, the 34 kilogram box, so the mass has to be mass 2. That always needs to correspond with the free body diagram it's referring to. So we break down the net force. It's the force of 1:2 plus the Fs max on 2, not total. It's the Fs max on that second box. And that's equal to 0 because the acceleration is 0. And so just like we had in part A, we have 2 forces that are equal and opposite, which means that we can draw the forces as being equal to each other in magnitude. So force 1:2 is equal in magnitude to Fs max 2. So now what we can do is we can break down Fs max 2. That becomes mu s times Fn2. And we know that Fn2 is Fg2 because, again, there's no vertical acceleration and there's no other forces acting vertically. So those are equal and opposite forces, which means that mu s times m2g, force of gravity is mass times g. So we just break that down, and now we can sub those values in. We have a coefficient of static friction of 0.35. We have a mass of 34 kilograms and a g value of 9.8 meters per second squared, which g is always when we're close to Earth's surface. We get a final answer of 116.62 newtons. So now what we can do is we can conclude. Therefore, the larger box, this is the force that the larger box exerts on the smaller box. So therefore, the larger box exerts a force of 2 significant digits, so 1.2 times 10 to the 2 newtons, forwards or to the right on the smaller box. So again, because we said to the right was positive and forwards, if you said forward, that would have been fine as well. But right is what the question is referring to, so that's also correct. So there's our solution where we started breaking it down and getting a number, and our statement is at the very end. And if you look at that force of 1:2, that was Fs max 2, and you compare that back to Fs max 1, it's the fraction of mass 2 to the total mass, as hopefully you would expect. Now we look at part C. Part C says if a person can push with a force of 350 newtons right, and the coefficient of kinetic friction is 0.30, what will the acceleration of the 2 boxes be? Now note that we have the same free body diagrams with a few key differences here. The first thing is that applied force is a little bit larger because we've had to get the object moving. So we've gone past the number that we had to get it moving. And then the other thing to note is that we don't have maximum static forces of friction anymore. Now these are kinetic forces of friction. Now these are going to be slightly smaller values in this case. And the reason they're going to be slightly smaller is because they're based on a lower coefficient of friction. Keep in mind that the coefficient of kinetic friction is always less than the coefficient of static friction. So there we go. Our free body diagrams look like that. And what we want to do, because we're talking about the acceleration of the 2 boxes, we're going to draw a system free body diagram. All the masses combined, in this case the 2 masses combined. So we have a force of gravity acting down on these two boxes, the force of gravity total, which is going to be equal and opposite to the normal force that's acting upwards on those two boxes, so the normal force total. And then horizontally, we have that force that was being pushed on the first box, on the 52 kilogram box to the right, but that acts on the system. And then there's this force of kinetic friction total on both of the boxes. And those internal forces, F1 on 2 and F2 on 1, do not show up on the system free body diagram, just like we had in A, because those are internal equal and opposite forces that cancel out. So we write down our givens. They're the same masses as before, but now we have an applied force that's 350 newtons to the right. Our coefficient of kinetic friction is 0.30. And our required value here is we're required to find the acceleration. So that's A with the vector on top of that. We want to know the magnitude and direction of that acceleration. So what's our analysis? We're always going to start from the free body diagram with F net equals ma. So the net force is equal to the total mass times acceleration because it's the system free body diagram. We're using the total mass. Now I'm going to say to the right is positive and forwards, as I've done before. But here we can't set these two forces equal to each other because the acceleration is not zero. We have to go ahead and solve for acceleration by dividing both sides by the total mass. Now at this point we know what FA1 is, we were given that, but we don't know what the force of kinetic friction is. And so what we have to do is we have to say the coefficient force of kinetic friction total is mu k times Fn total, because we're talking about the system. But Fn is equal to Fg, because there's no vertical acceleration again. And we can break this down to m total times g, which gives me 0.3 times the mass total was 86 kilograms times 9.8 meters per second squared. And so what I get a final answer of is I get a final answer of 252.84 newtons, 252.84. Now what we do is we have to sub that back into the other equation that we developed before. Now we'll notice as well that when we sub that in, because it's acting backwards, it's a minus value that we're going to sub it in as, a negative value. So the FA1 is a positive value because it's acting in the forward direction. And then now we put the kinetic force of friction in the negative, as a negative value. So we add a positive to a negative, we divide that by our total mass, and our acceleration is solving that equation. So we add those two things together, 350 plus negative 252, divide by 86 kilograms, we get 1.129 meters per second squared. That positive means that it's to the right or forwards. So now we can write our final statement. That's our solution. Now we can write our statement. And our statement is simply this. Therefore, the boxes will accelerate, and we need to put this to two significant digits. So it's at 1.1 meter per second squared to the right or forwards. Now we reflect on that answer. A 350 Newton force is about half of someone's weight worth of force. The coefficient of kinetic friction of 0.3 is about what we would expect a box on a smooth floor to be. And so if I push with half my weight, it's not going to accelerate that quickly. So 1.1 meters per second squared right seems to make sense. If this was helpful, please like and subscribe, especially because I've got some other videos that are coming out in regards to two masses together with a rope in between and a pulley problem. If you want to see a pulley problem with a little twist in it, check out the video on the right. For more on forces with angles, check out the video on the left. Thanks so much for watching.